something like this. This is a hyperbola. So what this is just, again, you have 2 points which are called the foci, and now the distance, like for any point D, CB minus CA is fixed, like the absolute value of CB minus CA is fixed. That's a hyperbola. Earlier we had
Difference.
the sum. Yeah, earlier we had the sum,
Okay.
now we have the difference.
Okay.
And these are three, and the last is something called a parabola. This you may have seen in quadratic equations and all. So this is a
Yeah.
parabola. So now what is the property of a parabola? You have again a focus and a director. So if you take any point on
I
the
think the distance would be the same from the focus to the directrix.
yes,
Okay.
so the distance AB is the same as the distance AC. This is actually a special case. You can think of it intuitively as a special case of an ellipse or a special case of a hyperbola as well, where one of the foci goes to the point at infinity.
Yeah, yeah.
Because then for an ellipse, if you imagine it, the point at infinity is along this line, then this distance plus this distance should stay fixed. Except AB plus AC is the perpendicular, and that distance is the distance of the perpendicular. It's kind of vague, but I think you may kind of see it intuitively.
Can you repeat that infinity thing?
Like, okay, it's very vague. Like, it's not a proper subcase. That's why I'm just trying. Okay, if you have some point along infinity along this line, then dA plus dB
Line
is dA.
AC.
Yes, then dA plus dB is DC, right? DC, right?
Yeah, yeah,
Yeah.
right. Because any point will have the same the focus
Yes,
and the directrix.
yes, but now you can say that the point at infinity to a perpendicular line is a fixed distance along that, along the
Oh,
perpendicular. It's kind of intuitive. It's not like a proper thing, but I'm just
Yeah,
trying
yeah, intuitive.
intuitively, if that makes sense. This is, again, you can do it for a hyperbola as well. Make the point at infinity on the other side. Got it?
Hmm.
Like, then the distance becomes again the perpendicular. Okay. Uh, yeah. Now I think we can start. It's 7. Is it okay if I start?
yeah.
Okay,
Yeah,
great.
all right. 21 people are joined, so we can start.
Okay, great. So we are basically working with with a structure called conics. So let's look at a special kind of conic called an ellipse. We have 2 points on the ellipse, and we have 2 points. How we define an ellipse is we have 2 points A and B, and the set of all points C such that AC plus CB is a given fixed distance. That is okay.
So AB,
Yeah.
AC and BC are fixed. AC
Uh,
plus BC, AC plus BC.
yes, as C
Okay, okay.
varies, AC plus BC is fixed. So this uh, line AB is called the major axis of the uh, ellipse. And you can see, obviously, it will be this ellipse is symmetrical along its perpendicular bisector as well, right?
Yeah, right, right.
So it's called the minor axis. These are the two axes of symmetry of the ellipse: the major axis and the minor axis. Now,
Yeah.
let's look at what happens if we take a tangent from C. So now you remember, right? Like CA plus CB is some fixed distance. Now I have the first claim I have. If I take some point here, D, and some point here, E, then angle ACD, and angle BCE are the same. Okay, can anyone try to prove this?
I already know the proof. It was in the notes you gave, that book.
That's okay. If yeah, I'll probably be going over the first things on the first chapter only. But if anybody who has not seen can try to think of what could be happening.
Yeah, yeah. D and E are any points? Arbitrary?
On the tangent, on the
Okay.
tangent from C.
So it does not necessarily DC and CE are equal.
No, no, no. I mean, we are not even talking about, like, it can be any point on the
Okay.
angle won't change, right?
Yeah.
Like I could make the chair here. The angle is not.
Maybe we can prove congruent DAC and CBE. Can
How would
we?
you go about that?
Yeah.
I mean, we don't
This.
have.
D and E
Yeah.
are
We don't have
varying, so that doesn't make sense.
Yeah.
And we aren't even concerned about D and E.
Yeah. So,
Yeah. And these two triangles don't look like congruent.
yeah, I mean, I can change T and D. It won't matter. So, obviously, ACD is ECF, right? Because vertically opposite angles. Now, you basically want to prove that BCF has the angle bisector CE, right? Or
Oh yeah.
basically,
Yeah.
the claim is equivalent to saying ACB, the tangent is the exterior angle bisector of ACB.
Yeah.
I think I got a proof.
Okay, great. Go on.
So we I don't define F line AC. Uh, I don't define F here, and I take the tangent line at C. Let's call it T. So
Okay.
we know by physics that the minimum distance says that AC plus CB. The point on T says that AC plus CB is minimum, is the one in which T is the external bisector of ACB,
Okay.
and so uh, and any
What?
point outside the ellipse will have AC plus CB greater than what we have right now. So the minimum must be achieved at the ellipse, and so we are done.
Okay. So 2 points in that. One of that is like, okay, there are two claims you made that along any point outside the ellipse, any point outside the ellipse, the distance is larger. Correct?
Yeah, I mean, yeah, we would
Vice.
have to show that, but
The distance is larger. We know that.
Yes.
That is known fact.
No, no, no. Okay. I mean, it's intuitively true, but can anyone tell me formally?
Yeah, we let
By
AF
triangle
intersect.
inequality.
We let AF intersect the ellipse, and then
Okay.
do something.
And
Yeah.
then join the Foki FB,
Okay.
and then GB we can also join, I think. And
Okay.
then FGB is a triangle, so maybe we can use triangle inequality FB. Then FB is smaller than FG plus GB.
Yes.
So
Perfect.
yeah,
Yeah. And that's it.
yeah, because now the sum is sum A AG plus GB is the sum, so we are done.
Yeah. Great. That is exactly right. So you're right. Okay. Now the other claim was by physics. We know that the point such that this the shortest distance on a particular line is the point where it's the exterior angle by is it's the angle bisector. Can you like show it by why is that true? Why is that
Yeah,
physics?
we reflect A across T, and then join B A dash and do stuff like that. And triangle inequality finishes. That.
Yeah, exactly. So the claim is that if you reflect B across CE, now when the distance AC plus CB as C moves along the line is AC plus CB dash, but that is minimized when at AB dash, right? Because it's true when C is like on the line AB dash by triangle inequality.
Here we have CB and CB prime are equal because
Yes,
the
B
reflection.
is yes, exactly.
So yeah, okay, okay.
Yeah, by triangle inequality, AC plus CB dash is less than equal to AB dash. Sorry, greater than equal to AB dash, and equality is when C is on AB dash.
You're right.
So, so C B dash BCE is ECB dash because of reflection, and we are done. And that's the claim. Okay, great. Now we have this. Now, what else can we say about these points? Let's see. Let me take another tangent from another point. Sorry, and let me take a tangent from here. I'll remove this. Yeah, and I consider this point D. Now let's see what else we can say. F A C. We just found two claims that we now want to prove. One is FDA is equal to BDC, and the other is that the angle bisector of FAC passes through D.
So basically A and B are isogonal.
Yes, yes, exactly.
Oh, okay.
Okay, so now you mentioned the isogonality. So that would motivate you to think of something. That should
You're
motivate you
right.
to think
Angle
of
bisector.
no, just
Isogonal conjugates. Like,
orthogonal conjugates. It's basically saying, or
Oh,
in any polygon that you have isogonal conjugates, you're basically saying that there's an ellipse at A and B that is tangent to the three sides or the four sides or the sides of the polygon.
that is a general definition.
That
We
is the
got the
general.
structured definition in all the books because we don't know ellipse at that time.
Yes, and that is how you define isogonal conjugates. There's an
Yeah, that's why it has a weird name like that.
I don't know about that. I mean, yeah. So this is basically the claim. Can you try to prove this?
We can prove that A and B are isogonal with respect to that angle, but I don't know how to prove that angle, like angle FAC is bisected.
Yeah, okay. Let's first go about either side. How do you prove that A and B are isogonal?
You first, we already know that exterior angle property, and then you have to reflect A in this line FD and B in this line CD, and
Okay,
you will get
just slow down. Let me reflect them. Okay, I reflected them. Now what?
point A dash FB are collinear,
Okay,
and we have that A dash B equal to AB dash.
why is that true?
Because of the definition of ellipse, and we
Great,
reflected.
great. Go on.
Um, After that, we see that triangles. Just a second. Let me see.
Yeah, yeah, take your time.
Yeah, triangles A dash B D and triangles
Yeah, they are
A
usually
B dash
congruent.
D are congruent. Yeah.
Yeah,
Why is this true?
Uh,
Why is
uh,
A dash A B dash is correct?
SSS.
Why is DA equal DB?
No, D is no. I said other order. DA is equal to DB dash.
DA is DB dash. Okay, DA is DB dash and DB is DA dash.
Oh, sorry. I
Sorry,
said the opposite. DA is DA dash and DB is DB dash.
perfect. That's the correct claim. So now observe that DAB dash is congruent to DA dash B because DA is DA dash because of reflection and DB is DB dash. So angle ADB dash is same as angle BDA dash, which means angle A dash DA is angle BDB dash. But now this is just the angle bisector, so we get FDA is BDC. Does everyone follow?
Yes.
Okay, great. Now the other claim of the angle bisector is, oh yeah, sure. I'll repeat. Observe that. Do you see why the congruency is true? Okay. If the congruency is true, we have that this angle is this angle, right? Because of the congruency. But ADB is the same angle, so I'll remove that. And now we know that A dash DA is BDB dash.
yeah, because of angle bisector.
And now because of angle bisector, we can conclude.
Oh yeah, so we have also proved that bisecting thing, because we have that angle A dash AD is equal to angle. Yeah, I
Yes,
think we are
you have the idea. See, because of the congruency, we also have DAB dash is what angle? DA
DB.
dash B,
Oh yeah.
which is same as saying DA dash F. But because A dash is just reflection, that's just angle FAD.
Yeah.
See, this is the argument. You have DAB dash is DA dash B because of congruency, but FA dash D is same as FAD, and you get your angle property. Does everyone follow?
Yeah.
Yeah,
Yes.
fine.
Okay. Now, let's
So
see.
when did we show that the lines are concurrent? We just
Uh,
assume they're concurrent and then we prove the rest of the properties.
what concurrency?
So the two tangents and their angle bisectors.
No, no, I have no,
If you
I'm not
see,
taken, I'm just taking the intersection of the, uh, what do we call it, the tangents.
oh, okay, okay, yes, I understood. Yes,
Yeah, I'm assuming that the tangents concur because I'm not assuming the parallel case for simplicity. You can do that, it's just perpendicular and that's not very interesting. Okay, we see a bunch of properties, right? Does everyone get the idea of a few properties that we're seeing here?
Yeah.
Like which idea?
I mean, do you, I mean, do you see the properties? Do you understand what's going on and how we can?
Yeah, there are just two properties so far, so we
Yeah,
get
yeah,
the idea.
yeah, great. So now, can you prove that if there's a triangle, if there are two isogonal conjugates A, B in a triangle, that implies that they are part of the ellipse, that they form, uh, they are the foci of an ellipse tangent to the three sides.
So all that means we have to prove that if we have two isogonal conjugates A and B in a triangle, then then the ellipse center at the foci A and B are tangent to the sides.
Yes.
Okay.
Yeah, I think we can prove that.
How?
That would require the converse of this thing we just
First,
proved.
no, I think for the regress proof, what we can do is that we can first reflect A in DG, which we have already done, which is A dash, and after that we can mark the intersection of BA dash as E. So that would by our, oh sorry, it is F I think in the figure. So it would by our construction mean that angle AFB is like externally bisected by DG, and we can similarly construct C, and then our ellipse is constructed because h must automatically lie because of the
Yeah,
isogonal conjugate property.
yeah, that sounds correct. So, okay,
Yeah, because we are
the
just have to prove that the tangent points are like say AF and AFB are the sum. We have to
And
prove the sum equal.
that can be proved by SAS congruence because if you assume the isogonal thing is true, then again those two triangles will be congruent.
yeah,
Yeah, yeah.
he's right about that. That follows as he claims it does. Okay, now let's think of other ways to. Uh, you have you have heard the word that these are conics, right? That this is a conic or a conic section. What does that mean?
It is a section of cone.
Great, but why? Like, if I take a section of a cone, why is it forming this amazing structure called ellipse, where you have this amazing property?
It's like you cut the cone in
With a
some way.
plane.
Yeah, yeah, okay, great, but you're getting some shape. Why is it an ellipse? Why does it have this property that the distance from the two foci is a constant and there are two such foci? It's a pretty great property, right? But why is it happening?
I think it is quite intuitive because if we take the vertex of the cone at the top, then if we cut by a plane, then I think the plane we get a ellipse because of the cuttings of the mark on the plane.
No, no, no,
Uh,
yeah, you get a shape, and
yeah.
it looks like an ellipse. But why is it an ellipse? How do you prove that it's an ellipse?
By proving this, AF plus FB equals AC plus CB.
But you don't have any 2 points A and B, right? You're just given a shape.
Yeah, we will take that and we try to prove like rigorously.
Yeah, but that's okay. I mean, you're saying that such a thing should work. Like, we should be able to do this and do that. Like, there's a very simple proof, and that makes it very, like, that motivates a lot of further things we can do with it.
Okay, let me think.
Okay, it's like difficult to come up with, but it's a very clean idea.
I think from the center of the cone we have to drop a perpendicular to the plane.
What? Sorry.
From the center of the cone we have to drop a perpendicular to the plane.
From the center of the cone to. Okay, sure.
Uh, and intuitively, like I'm not 100% sure, but intuitively it is clear that it must be the center of the foci, like it seems.
Hmm.
I also have an idea. If we drop the perpendicular from the vertex of the cone to the conic, and then we draw the major axis. But major axis we know already, but we draw a line and then mark the points which are at equal distance from the midpoint, and those two are and then we establish properties of those 2 points, but that does not find like this.
Okay, I'll not actually tell you the proof of this. I'll leave you with something, and that you should be able to see how it works in 3D, because I cannot make a 3D thing here.
Yeah, okay, that would be good.
Okay, so let's say you have, okay. Let me just, you can try to extend it very naturally actually. So let's say you have these two lines, right? Instead of cone, you have these two lines, and I cut a plane like this. This is how the plane is cutting. These 2 points it cuts. Now I take the in circle. In the general structure, you will take an in square. Okay. Right now, I take an in circle. Oh, in circle. Oh, okay. I take an in circle and I take an X circle. How do I take an X circle? Hmm. Yeah, let me draw it. Take an X circle. Yeah. So I take an X circle and an in circle. In the general structure, I take an in square and an X square. Okay. Hello.
So in 3D, can you prove the existence of a sphere?
Okay, you just
I
take a
think
cone that is tangent, or just take a sphere that is
uh,
tangent to the sides of the cone and just move it along, and at some point it will be tangent. It's
yeah, yeah.
yeah. It,
And
okay,
here
so
also the encircle is homothetic to the x circle, so I think that would the proof is like that only.
no, it's like quite simple. See, we claim that the foci are the tangency points Q and R. In the general, that at the points which the plane is tangent to the spheres Q and R, we claim that these are the foci. Now see,
Okay.
Qn is what?
Is equal to ro.
Qn, no, you know that, but like Qn is Ns.
Yeah, yeah, that also.
And similarly, Rn is Rnu.
Yeah.
So the sum is Su, and that's fixed.
Oh, right, right.
And
Uh,
that's the
R
proof.
uh,
So Rn is equal to n, what is that, nu, and then q, then r, then what,
Rn
q.
is Nu because of
Yeah,
tangency.
yeah, yeah, yeah.
So Nq is Ns again because of tangency,
Hmm.
and then N Qn plus Rn is just Us, which is fixed.
Oh, yeah.
but this is only true for points N and O. What about any other point on line NO?
No, we are only talking about the the how do you generate a conic?
The tangencies. We are
By the
only talking about the tangencies.
you are talking about the points at which the sphere cuts the conic, right? Imagine this as a part of the conic,
Okay, okay, got it.
and now you can
And
consider that you're rotating this whole thing, and you and
Yeah,
that are
and
moving on.
these properties of circle would generalize to a sphere.
Yes, directly.
how can we rigorously prove the existence of a sphere inscribed in and this X sphere?
I mean, you do the same argument. Like, how do you generate? How do you write? How do you make a like? You just take a square, and because it's a continuous thing, you move it slightly, 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 and it's eventually tangent. That can be easily formalized. You can try to do that on your own.
Okay. So do you know any source from where I can see this in detail?
I think Akopian will probably mention something. You can look at it there.
Okay.
Okay, now let's see another few things. So if I cut this, like this is the line, I cut it here, let's say.
Sir, but if we check at a point other than N, then S and Q and U and R will lie in different planes, right?
Okay, so the thing is, you're only talking about like where it
Like
cuts
this is
the
special
plane, right?
case here, what we're checking.
You're
We are only we will cut the take the spheres to those points where the plane is tangent to the sphere.
yeah, but we are fixing the spheres initially. When we are taking the plane, we are making two spheres. It's right, and now of any sphere that's tangent to the cone is like tangent at a fixed height, right? The entire tangency line, this UW, for example, here, is at a fixed height. So the plane which is tangent is at a fixed height. Similarly, ST is at a fixed height.
Fixed height from which point?
I, a fixed distance from I.
Okay.
So US and WT, as you move across for the entire sphere, it's like a constant distance. You can show that the tangency point will be collinear, like that's easy.
Yeah, that is easy.
Yeah,
You can show
because you are just joining IN. Anyway, let's get to the main thing. Let's remember how in an parabola we had something called a directrix, right?
yeah.
Okay.
I didn't quite get that constant distance thing. Like from a point and a line, the distance is only one distance, so it is constant.
It's a plane in general, right? I'm saying for the entire plane that the plane, if you take any point at which the plane cuts the cone, it's equal distance. Like IU is equal to IW in this case.
If we visualize line LM like a plane, that would be good. That would be that would be then we would understand better.
Yeah, yeah.
Okay.
This is just very intuitive. Like you can generalize it to a 3D structure. Trying to give you the idea of what's happening. Don't don't take this that way. Okay, so now let me try to intersect ON with this line ST. In general, it will be the intersection of a plane at which the but here is the point, fine. uh, is everyone on board with this?
Yeah.
Yes.
Okay, let me drop a perpendicular from N to this,
From plane to the line, right?
N to the line, yes.
Okay.
From N2.
The line
Okay.
ST. Actually let me
ST is a plane or line right now.
okay, actually let me not do this. This will get too confusing with the this way. The kind of I'm not sure how to actually explain this. Let me see.
Actually, there is a 3D GeoGebra also.
Yeah, but I can't handle that, and it's like very heavy. I tried
Okay.
with that. Okay, let's get back to the main thing. I think we are distracting too much. You can actually show that. Okay, I'll just give you a gist of what's happening. Then you can actually make two lines. In this case, like a point V. So the distance of any point Vn by Vq will be fixed. So even any conic has a directrix, and just you just say that this ratio is fixed.
Yeah. So the if we take a point on a conic, then the ratio of distance from focus to the directrix is fixed, right?
Yes,
Okay.
right. So like Qn by Qv will be fixed. In this case, it's not a big thing because it's just one point. Like uh, Qo by Qn Qv is also the same. Something like that. You can find. Okay, let's get back to the main thing. I'll remove all this extra points. Okay, so let me take a few special cases now. I'll remove all this. Uh, yeah. Now I take a chord passing through it. Fine.
This is a chord.
Yeah, a chord of the ellipse. It,
Okay.
like DE is a chord, right, of the ellipse.
Okay.
Now, if I take the tangents from E and D, uh, let's make this a bit smaller. Yeah, F. Now, DFE. Can you say anything special about the point B or anything in here?
I think FD is equal to FE.
FD is equal to FE.
Yeah, it looks like.
Okay. Okay, that's a good claim. What else?
And maybe in like a circle, maybe BF is perpendicular to DE or
By the way, FD is, I think you can see more nicely now that FD is not FE, right?
can you repeat?
I think you should be able to see that FD is not FE.
Oh yeah.
Yeah, okay. Try to, okay, what, can you say anything at the point F with, in like relation to BDE?
You just gave, gave away one claim, I guess, that FA is perpendicular to DE.
Amazing. FA is perpendicular to DE. What else?
Why?
That's just a claim right now. Just a claim.
I don't know, but probably BEFD cyclic.
BEFD cyclic. Okay, let's see. Okay, I'll give it away. F is the uh, X BX center of BED, and A is the touch
Oh.
point of the X
Okay.
circle. See,
Then
because
FB. Then the in center will lie on FB, but that is not necessary, I think.
yeah, the incenter will lie on F. That's
Yeah.
true. So F is the, we just called it yeah, is the BX center, right? That's the claim.
Right.
Yeah,
So
that's easy to prove.
yes, because you have the exterior angle
The
bisector
angle
from F,
bisectors. Yeah. Yeah.
and you already know this. Now, can you prove that is the foot of the perpendicular.
Oh yeah, we can prove that because the angle DAE, which is 180 degree, must be bisected by FA, as you
Yeah, yeah,
proved earlier.
Yeah, yeah, exactly. So E, we know that in a general thing, like in the center of like the circle, what am I saying? The center, yeah, okay. Sorry, ignore that anyway. The Yeah, so we know that FA is the and FB are isogonal in EFD, right?
Yeah.
But FB, as we have claimed, is the angle bisector here of DBE. So remember by fact 5 that we have the uh, center of EDF on the line BF.
yeah, yeah. Uh, we if we take the circumcircle of DBE, that would where the line FB cut, that is the center.
Yes, you are
I think
claiming.
that is called the in center center lemma.
Okay, in center, X center lemma, whatever it's called. Anyway, so you know that this is the center, but
Yeah,
we know that we also know that in a general triangle, this line and this line are isogonal, like the line joining
yeah,
the center and the
yeah, I see.
altitude. And you can just frame it in terms of purely angles as well. But yeah, just to rush things along, I'm not doing that. Is that fine?
Can you repeat why say the foot of perpendicular?
We know that FA and FB are isogonal, right?
Yeah,
But FB is the line containing the circumcenter.
yeah.
That means the isogonal to it must be the altitude.
Oh yeah, got it.
Okay, great. So that implies the
So equal to the circumcenter.
yeah, exactly.
Okay.
Uh,
By the way, when you say fact 5, are you referring to some handout or book?
oh, okay. I mean, this in center X center lemma is often just called fact 5.
Okay.
Fact 5.
Yeah, I don't know why that's the name. It's just a name that's just used now. Okay, let me see what else. Yeah, okay. That reminds me. If now if I change this from an ellipse, okay, this you can take as a kind of an exercise. If I change this from an ellipse to a hyperbola, then the point at which the
That would
tangents
look
meet
interesting.
will be the incenter. Right now we have the excenter, then it will be the incenter.
Can you define hyperbolas?
Oh, sorry. Yeah. So right now we are
You don't.
saying that
You
the
have not yet defined hyperbola.
no, I have not.
Oh, okay.
I think
Yeah.
you defined the
Uh,
distance is constant,
yes,
modulus
I
of.
So,
yeah did that
differences in
before.
hyperbola. There is difference between the directrix and the focus.
Uh, Directrix. Okay, I'm just AD minus DB is fixed. You don't need the directrix.
Oh, okay.
Directrix you'll have a ratio actually. You won't have the difference. Anyway, AD minus DB is fixed.
Okay.
Yeah. Sorry, the modulus of AD minus DB. It may be minus A and plus A, whatever.
Yeah, yeah. I was trying to say that only.
Ah, okay. Okay. So now we've seen a bunch of properties on the ellipse. Okay. Let's first do a bunch of properties on the uh, parabola. Then, if we have time, we can look at even more interesting and fancier properties on the ellipse.
We are done with ellipse.
I have many things on the ellipse. I was thinking that we can do a bunch of basic things on the hyperbola first, and then we can
Okay,
get back to the ellipse.
that would be good.
Sorry, I'm
So,
saying hyperbola, parabola. I mean,
okay.
yeah, okay. So let's look at a few things on the parabola, and then later we'll get back to the ellipse if we have time. So a parabola is this structure where you have a focus again, a point called the focus. and a random line called a directrix. Uh, and it's the set of points such that BA this distance this distance. Great. Uh, is the definition of a parabola fine?
Yeah.
Okay. Now
Yeah,
again I
intuitive.
take yeah. Now I take a tangent.
You have drawn a circle there,
Yeah,
centered
I'm
B.
just saying. Yeah, I'm
Okay.
just saying BA is equal to BC, where C is the foot of the perpendicular from B to the line. And then the set of points such that BA equal BC is the parabola. Is that okay?
Yeah.
Okay.
So we
Now,
take a circle. We take a circle and then
no, no,
we
no,
draw a tangent.
no. You have a point A.
Okay.
You have a line L. Okay. You
Yeah,
have
yeah.
a point A and a line L. Now you want the set of points such B, so that when you take the perpendicular from B to this line and call it like the foot C, then BC equal BA. You're taking this set of points which satisfies this property. That's called the parabola. The set of points which has this property.
Yeah, perpendicular and must be equal to the to AC. Okay, I got it.
No, BA, not AC.
Yeah, yeah, yeah. BA, BA.
BA equal BC. Okay. Now let's again take a tangent because why not? Now, uh, the tangent is actually the angle bisector of BC. Can anyone prove this?
If we say that parabola, if we define a parabola to be an ellipse with one focus at infinity, then this is done, I guess.
Amazing. Yeah, that makes a lot of sense.
Yeah, yeah, yeah. Yeah, that's right. What Vedant said. I was also
Yeah,
thinking.
yeah, that's a very intuitive proof, and you can formalize it later on. I want to look at a bunch of other stuff. Now, BA equal BC as well, right? And this is the angle bisector. So if I take a foot of perpendicular from this here, let me call this D. Okay, well, oh, I've defined the tangent twice. Yeah. So let me take this point. Now D is the foot of the perpendicular as well, right? From A to this tangent, correct?
What?
Can you
What?
repeat?
Repeat.
D is the foot of the perpendicular from A to this tangent, right?
Yeah, yeah.
Okay.
A
Now
to
let's
which tangent?
from the B tangent.
Okay.
Okay. Now let me take three other points, like two other points, and again make tangents there. So let's say these two meet here and these two meet here. Correct? Is that correct?
Yeah.
Mm, okay, and sorry, these two don't. This tangent, yeah, and this, right? These points. You get GHI for a triangle, right?
Yeah, right.
GHI. Okay, so GHI has another point. Can you guess what point it is?
Has
A.
another point.
Boom.
Mm,
A.
GHIA is cyclic.
Yeah, yeah, yeah.
Can anyone prove that?
Previously we have AB. Uh, we have the bisector. I think. Where is the bisector? AB. Uh, BD bisects ABC, right?
BD bisects ABCS.
Okay. So that would also be true in for E, because E is also the tangent.
Yeah,
So let me think. It.
I have a hunch it would be some sort of angle chasing.
no
Yeah.
angle
Right.
chasing.
Actually, yeah.
No angle chasing at all.
Oh,
Oh.
Mm.
Try to use the point D.
D lies on the tangent to the vertex,
Sure.
and so does the perpendicular from A onto GE and onto IF, and like they all
Uh,
lie on the same
so
line. So
yeah.
Exactly.
they must
So the
be
Yeah.
Simpson line.
Radical. Yeah.
Yes.
Power of D.
No power. No power.
Simpson line.
that's the Simpson line.
Simpson line. Simpson line. Yeah. 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 Sorry. Sorry.
Yeah. See, for if you drop the perpendicular onto GI from A, that's basically the midpoint of AC,
Yeah. Yeah.
and so on. So line, there's a line joining the 3 points, the 3 feet of perpendicular, which is just like this at ratio
Simpson.
half,
Simpson wala's line.
and that's the Simpson line.
But if you drop a perpendicular to other like tangent, I don't think it is the midpoint.
No, the midpoint. Like, okay, if you draw it here, then this is the midpoint of these 2 points. J is the midpoint of AK, right, by a previous claim,
Yeah.
and so on. So, like, it's like the midline, like, okay, it just homothety half of the directrix.
Oh, got it.
All feet lie. So it's a you have the Simpson line and the cyclicity. That's really cool, right?
Yeah.
Now, okay.
That was really good.
Now, where will the ortho center of HIG lie?
Bisector of the Simpson line.
Bisector of the Simpson line?
Yeah. There's a lemma, I think.
Yeah, you're saying that the Simpson line bisects AH.
Yeah.
Or
Yeah. Yeah.
here. Yeah,
So,
so it will lie on the directrix.
yeah.
So the ortho center always lies on the directrix.
Yeah. Right. So we are studying like triangles in view of conics.
Yeah. So also, because now if you have you can generalize this. You can say that if you have any triangle and any point on the circumcircle, there's an in parabola with that as the focus.
Please repeat. If we
You
have
can
a triangle.
say that there's an in parabola with
Yeah.
A as the focus for any triangle GIH if A is a point on the
Oh.
circumference.
Okay. Okay.
Cool, right? Like such ridiculousness, things you would never expect, kind of. Okay, let me give you an exercise. You have that this is cyclicity. I told you. Okay, great. So I have two lines now. I have two lines. This may be a result from physics. I don't know if it is there. You have a person here on this line and a person here on this line. These two lines are fixed. Okay, a person E and a person F on each of the lines. Okay, now E
Yeah.
is moving at some constant speed, F is moving at some constant speed. So as E and F move, the line EF always remains tangent to a fixed a fixed parabola.
Can you repeat?
E is some point on this line, F is some point on this line. Some person, okay? Think of these as two roads. E is a person on this road, F is a person on this road. E is moving along this road at a fixed speed. F is moving along this road as a fixed speed. Okay.
Yeah.
Now make the line EF. At any point, EF is tangent to some fixed hyperbola. Sorry, parabola. Why do I keep saying hyperbola? To
And
some
are the
fixed.
speeds of E comma F same?
No, they have some speeds. Both have some of their own speeds. They're moving at a constant speed. That's all you know. F is moving at a constant speed. E is moving at its own constant speed.
Is the speed really required?
What do you mean?
Like you said, constant speed. If we have some other speed, then will this hold? Or so I'm just saying that to solve the problem, is speed really required?
I mean, that would basically be saying for any point here and any point on this line, you have a tangent. That's just
Yeah, yeah.
ridiculous.
I was saying, I was
Are
asking for
they
that.
are the speeds the same constant or different?
No, they're just some constants.
Are they
Basically,
different?
we have to just vary the points on the lines, and we
Yeah,
have to prove that there will be a parabola tangent to the point to the
yeah,
line.
yeah. That's pretty much it. Yeah.
So the parabola will have the focus on the intersection of the lines.
Why? Oh, they do not need to pass through the intersection at the same time, right? So you're basically saying like at some point that the lines will become this and this. They're basically saying lines passing through the focus are tangent to the parabola.
Yeah.
That's just not true, right?
Oh, yeah.
You cannot make tangents from the focus to the parabola.
Uh-huh.
I think all such lines, this EF while moving must pass through some point, which is I think midpoint of EF.
Uh, I didn't. You're saying that as E and F move, the midpoint of EF remains same.
Yeah.
That's just not true, right? Like you're basically saying, let's say,
Yeah, that is not
let,
true because the
you,
distance between A and E will increase.
I mean, it's possible that F is moving along this direction and E is also moving along this direction.
Okay. So I think they will be moving in the same direction.
They can be moving in opposite directions. It's totally fine.
Okay.
I think I got it.
Oh, do tell.
Uh, uh, I don't know for sure whether I'm correct, but F is moving linearly on some line and E is moving linearly on some line.
Correct.
So there, suppose we name the intersection as A, so the perpendicular bisector of AF will be linear,
Sorry, the perpendicular bisector of.
uh, of GF will be linearly moving,
Okay, sure.
and the perpendicular bisector of GE will be linearly moving.
Okay,
So their intersection must be linear,
okay.
and so O must lie along a line.
No, I don't think this is true. By the way, let's just check uh, because it's right. Like I don't think it will be linear because you are moving two things. So like intersection of two linear things is a degree two thing.
Okay.
Uh, So By the way, conics are just degree two curves, by the way. So if you can like write an any equation in x square, y square, x, y, and a constant, that will form a conic. That's something you can prove.
Yeah.
Okay, so how many of you are familiar with spiral similarity?
Are just mm, intuitively clear that we take a triangle, we make a homothetic triangle, which is and then we rotate.
Okay, so you can I'm assuming that E eventually goes to J and I eventually goes to F. That's
Oh,
fine,
okay,
right?
okay. So
For
what is
simplicity,
center? Center is the intersection.
I take no, I take these two circles, G
Oh,
E
this,
F
yeah, I know this. I've seen this figure.
G I J. So you can remark that K is the center of spiral similarity. So as like E and F move, this circle will always be there. G, G, K, G, and whatever those points are. Okay.
Can you repeat your last line, this kg thing?
Like if I take another like line here, like F say goes eventually to like F eventually goes to L, then if you take the circle K, G, L and let it intersect here, this will be where E has gone to. This is a result of spiral similarity, right? Because
Yeah,
the same spiral similarity is taking, which takes IG to EF, the same center takes IG to ML,
yeah,
and
okay. This is clear intuitively because we just rotate the triangle.
yeah, and then you expand, so this becomes true. So this is also a circle.
I'm not quite sure why spiral similarity gives this.
Okay, what's the issue exactly?
So can you explain the similarity again?
E- okay, I mean, I take I say E eventually goes to J and F eventually goes to I. I consider the circles I, J, G, K, and I even consider the circles E, F, G, and let them intersect at K. Then K is the center of the spiral similarity as I, J are moving. Like E and F are moving. K is the center of the spiral similarity. So like if F goes eventually to L, then I can draw the circle K, G, L and it M. Then E would have gone to M this period of time.
But why would I be gone to M?
That's like a result of the spiral similarity, right? Like FL to EM is K FL to EM is KF by KE is equal to KL by KM, and KF by KE is KJ by KI, which is uh, this ratio
We can understand this
FI.
more better in a better way by saying this. Let take the center at K first, and then under spiral symmetry, I J G maps to J E F, and then we take a homothety G, which sends G E F to G M I. That's all.
I guess so, yeah. That makes sense.
But how can we do that? First, we like taking spiral similarity at K and then homothety at G.
G पे ले सकते हैं मतलब कि we can take G at G because see that F E
I
is
don't think we
parallel to
can.
LM.
I don't think we can take homothety at G. That's why it's like important that spiral similarity is there because they don't need to pass through G at the same time.
Okay,
If they
I
were
thought.
passing through G at the same time, then you will just get a bunch of parallel lines and the center of the spiral similarity will be G itself.
Okay, okay. No, the triangles G E F and G M L are looking like homothetic or similar triangles. So that's
No,
why
no,
I
no,
said.
no, they are not. I mean, yeah, they're not. Okay, I can make this. No, they're not. Right?
Yeah, yeah. Okay, okay.
Yeah. So, yeah, they're not. Because the spiral similarity is at k.
Okay.
So we know now this is the center of the spiral similarity. We can now remember, we can now remark that k is the focus of the parabola that we want.
But have you proved that points KGLM are concyclic?
Yes, that's just a result of the spiral similarity. I don't. I will have to prove to you the results of to you how spiral similarity works. I
No, I
don't.
know
We
spiral
can look at it.
similarity.
Yeah.
We
So
can look at
okay.
it.
Okay. So remember that f went to I and e went to j, right?
Yeah,
So fi by ej is a constant
yeah,
as f and e vary because of the constant speeds. So fi by ej because of the spiral similarity is what? Kf by ke,
oh yeah,
because it's kf by ke. So kf by ke is a fixed ratio, and
Yeah,
that's
and that
true.
simply
Kn by
says that
km is also same as
there is
kf
a
by
parabola
ke.
actually. Yeah. Okay. Okay.
but this ratio might be same for different case.
This ratio is just true for the 1k because that's the spiral similarity center.
No, no, K
And
is unique, so that cannot be true for all any case.
Okay,
you can,
Anytime K is the K can only be the intersection of the circles I, J, G, and G, F. So K is unique.
yeah. Okay, let's not spend too much time on this. So now remember that uh, if I drop the perpendicular here and if I drop the perpendicular here, remember that in the Mickel, the feet of the perpendicular are collinear. If you drop feet of the perpendicular from the Mickel point, the feet of the perpendicular are collinear. You remember this, you must know this result, right? If you drop the feet of the perpendicular onto the diagonals and the two sides,
It's
and
called the Gauss line, right?
yeah, the Gauss line, these are collinear.
You take the equal point in the quadrilateral.
Yeah, yeah. Now
Which
it's
quadrilateral?
k is basically the Mickel point of ef ji, right?
Oh,
Like
okay.
ef ij. So yeah, so this line is collinear. So that's like, just like the line op. Op is a fixed line. So the feet of the perpendicular all lie on a fixed line, right?
Yeah, yeah, yeah.
So if I take the ratio 2 and you can even get the directrix of what will be the line.
Uh,
And
mhm.
now you can reproduce this because the feet of now you can just finish using this. The feet of the perpendicular will be collinear, and you can reverse engineer the result we previously had. Cool.
Yeah,
Yeah,
these were quite interesting.
yeah, it is very nice. I didn't want to spend as much time on this as we did, but yeah, I think it was important too.
There will be a handout also.
You can use you have been provided a resource book, right? You can read
Yeah,
the
yeah.
chapter one.
Copy, copy. Geometry of conics.
Yeah, you can read the chapter, first chapter.
Mm.
Okay. Well, next we have another 20-25 minutes, so we'll try to look at some more interesting stuff. Okay, first thing you must now know is that if you have the tangents as before, if you have a quadrilateral with an in parabola, then the focus is the Mickel point, correct?
Yeah.
Yeah. So if you have a quadrilateral with an in parabola, then the center of the focus of that parabola will be the Mickel point.
Yeah, you are talking about the quadrilateral IEFJ.
Yeah, IFEJ. Yeah.
Okay.
So that's one thing. Now let's. Uh, so how much time do we have?
Class will end at 8:30, I guess.
Okay, 20 minutes. Uh, I think we
20.
can do this. Okay, I think we can do this. Let's get back to our very nice old thing called an ellipse. Where's my ellipse? Yeah, there we go. Okay. So first result that if you have I think we skipped a bunch of stuff as well. Okay, let's go through that pretty fast. If you take these are two parallel chords of the ellipse. Okay, we'll not be going. The results on the ellipse can actually be pretty much similar. Are pretty similar to the results
Yeah, because that is only a limiting case of the ellipse.
on the hyperbola. I mean,
Yeah.
ellipse and hyperbola have pretty similar results. You can reproduce them on your
If we can just take E and F to infinity, we get a hyperbola.
own. Not time to. Okay, yeah, I
Is
guess
that not right?
so. Wait, yeah, but that's yeah, okay, yeah, that makes sense, but it's a weird way to think about it. But sure,
Yeah.
yeah,
Okay, okay.
yeah, okay. So anyway, let's get back to the main thing. Uh, Now K and L are the midpoints of these chords. These are two parallel chords, and K and L are the midpoints. Then KL passes through the center of the ellipse.
Center of the
Where?
major axis EF.
Yeah, it's
Is it
also
okay?
called the center of the ellipse, the
Yeah.
intersection of the axes or whatever you want to say. M is the center of the ellipse. Yeah, yeah, sure. Is this fine? Like what the point M is, right? So this is the claim. Can someone try to prove this? Oh, GH and IJ are two parallel chords of the ellipse. K is the midpoint of IJ, L is the midpoint of GH, KML are collinear. This is the claim. Can you prove it?
Okay. So J, M, G are not collinear.
J, M, G are not collinear. Yeah, you can vary I, right?
No, but M will also vary because M is the
M is the
uh,
center of the ellipse. It's a fixed thing. K
So
varies.
we can do this since like a ellipse is like a scaled circle on one axis.
Perfect. How do you formalize that?
Uh, so I don't know how to say that formally. It's like in coordinate version, I remember it. Here I don't.
Okay.
Uh,
Okay.
I
Okay.
can I can formalize that, I think,
Okay.
because we know that midpoints of parallel chords lie on a line on a circle.
Yeah.
If we just linearly expand the plane in one axis, the same will hold.
Uh, sure, I guess. Okay. This is the okay. I'll tell you how to do this. Remember that we were taking conic sections, right? We said
Yeah.
claim that an ellipse is a conic section.
yeah,
One
right.
thing nice about what if you take the top of a cone to the point at infinity? What happens now?
It becomes like a cylinder.
Yeah. So you can actually formally get that any ellipse at all, is a cylinder cutting a plane.
Any ellipse is a cylinder. Oh,
Cutting a,
cylinder cutting. Got it.
like the intersection of a plane and a cylinder.
Yeah.
Okay. So now what do you do?
So you project it onto a circle.
Exactly, exactly.
Yeah,
So
project.
yeah, so you have a plane, project or it onto a plane that is like perpendicular to this side of the or whatever to the base of the cylinder. Let's say let's project it onto the base of the cylinder, right?
What? We take a cylinder first, and then we cut it with a plane, and then project on the base.
Yes, perfect.
Okay.
Parallel line goes to parallel line because you're just taking the feet, right?
Yeah.
Parallel lines go to parallel lines, and the center goes to the center,
Oh yes, yes. Right.
and that's the claim. Collinearity. There you go. This is your first experience with what's called a projective transform.
Oh yeah, yeah. Projective geometry. I was thinking about that.
And that's how you claim that KML are collinear. It's an intersection of a cylinder with a plane, so just project it onto the base, and you're done.
So this is called projective transformation.
A projective transformation is taking at any point
Yeah.
and taking a plane. You have a plane, right?
Yeah. Okay.
You take a point outside the plane,
Outside the plane. So
outside the
where?
plane
Outside the plane.
in the 3D space, right?
Okay. Okay.
And you make all the lines from that point onto the plane.
Oh, so parallel lines would intersect at the infinity. So that is
Yeah,
saying like.
yeah. So now
Oh,
what you do is you take another plane, a different plane, and let these lines intersect that plane. The lines you had, let it intersect the different plane, and you get what's called a projective transform.
okay. So the point at infinity lies in that plane.
Yeah, the point at infinity can perhaps lie in that plane because
Okay.
it the new plane does not need to be parallel to the old plane, and
Hmm,
that's
okay.
what a and
So
that's
here
what
in
a
ellipse to circular point is at infinity.
yeah. But now we just projected it onto a plane
Yes, sir. So
perpendicular,
like
right?
in the method you told we're projecting like one point and two planes. Here the point is at infinity.
Yeah, yeah. The point you are projecting from is at infinity. Yes,
Oh, yes.
correct. So yeah, that was the idea. Pretty cool, right?
Yeah, yeah, right, right.
Okay. Now let's see a few other results that I kind of forgot to share. You remember there's something called a 6-point circle, right? You may have heard of it.
Yeah, 6 point circle, yeah.
Okay. So what
It
you do
is
is
like
that
a
you
7 point
drop the
circle.
perpendicular onto sides, right? You drop the perpendicular onto the sides from like two like isogonal conjugates onto each side, and you then claim that these points, all 6 points, like if you have a triangle, then all 6 points are at an equal are on a circle centered at the midpoint of K and L. Prove it.
So can you say the result again?
If I take any tangent on an ellipse, then you. Oh, sorry, I'm going crazy. Yes, he's correct. Sudarshan is correct, of course. Uh, Perpendiculars from E and F, of course. Now, if I take
Yeah,
the
because
perpendicular,
E and F are actually isogonal conjugates, not A
yeah,
and F.
yeah, yeah. I was being weird. I don't know. So, if I take any tangent and drop the feet from E and F. The distance the distance mk and the distance mil are some fixed constants uh, which are not dependent on the position of I. Or you can say that as I varies, the feet of the perpendicular onto the tangents from E and F lie on a fixed circle. Can you prove this?
We can just reflect f about the tangent,
Yes.
and then we know if the point is f dash, then we know that ei f dash is collinear.
Yes.
And then like just taking homothety ratio half centered at f, that like ef dash becomes lm, and the
Yeah.
length of lm is also fixed.
Yes. Perfect.
Yeah.
You remember that when we reflect f, now lm is half of ef dash, but ef dash is just the fixed distance on the or the sum of the distance on the ellipse. So ml is half of that.
What is half of that?
So that's a
Oh,
fixed
under
distance.
homotopy at EF.
Yes, you can take it as homothety or just like midpoint theorem, whatever.
Yeah, yeah, midpoint theorem. Yeah.
So ml is half of ef dash, so ml is a fixed distance. So any like the feet of perpendicular are at a fixed distance from the center of the ellipse, and that's the result. Sounds fine?
Hmm. This was also
Okay.
interesting because we have a point and we vary that on an conic and we could get a circle suddenly.
Yeah, it's pretty awesome. Okay. We have 10 minutes, right? Okay, let's do this actually. Why not? Let me delete this as well. The Michael points were being very nice, right? When we were taking ellipses and parabolas, right? The Michael points of in the thing. So let's take 4 points. Let's take this, and let's draw the tangents. Okay. Yes, so you have 4 points, right? G H I J. G H I J is a quadrilateral with in ellipse this. Okay.
Yeah, right.
Now A and B are isogonal conjugates.
Yeah.
So prove that if in any uh, quadrilateral there's a point A which has an isogonal conjugate. If it has an isogonal conjugate, then GAH plus JAI is 180. Or if it has an isogonal, you can, by the way, you can reproduce the previous logic that if A has an isogonal conjugate, then these form the foci of an ellipse which is tangent to the four sides. So now prove that GAH plus JHI is 180. Yeah. Can anyone tell the proof? Any ideas?
Yeah, doesn't it follow from the angle bisector thing we proved in the beginning
Yeah, how?
that AJ is the angle bisector of DAE, and we get
Okay.
that GAH plus JAI is one half the angles around A, which is 180 degrees.
Perfect. So what we are basically changing our claim is that GAJ plus HAI is the same as this angle, and because these two sum to 360, if this sum plus this sum is this sum plus this sum,
Yeah.
then
We use
they will have,
so
yeah.
G. So you draw a G. That was the bisector, right?
Yes, so yeah, let me just
Oh yeah.
complete.
Then that this follows directly.
Yes, so we now GAH, this triangle plus this triangle has angle sum 180, 180 plus 180, that's 360, but this angle plus this angle is half, like, right?
Yeah. Yeah. Yes.
And you can reproduce, like, what was it? Yeah, DAC and this angle. So yeah, and that makes your claim true. Okay, great. Now we have this. So one last thing I'll show and I'll conclude after that. I'll not prove it. That now if you take the Mikkel point of this quadrilateral, this is the Mikkel point. Then mg into mi is mh into mj. That's just the similarity result. But also ma into mb and GAIB also has M as the Mikkel point, and so does HABJ. Also, not just that, you have this, but also they have the same angle bisectors. HM, the angle bisector of HMJ, the angle bisector of GMI, and the angle bisector AMB is the same. Not just this. There
Which angle bisectors? Sorry.
are uh, the angle bisector of HMJ, GMI, and the A and B. These are three same angle bisectors.
Oh. Okay.
And MA into MB is MH into MJ is equal to MG into MI. And if you this is also true if you replace A and B with 2 points you can define as such. Take the circles HAI and circles GAJ. Okay, you'll get a different point N. Okay, now take the circle JNI and the circle G and H. These will you get another point, right? Hello, you
Can
took
you
the circle,
repeat this last thing?
you took the circle GAJ and the circle HAI. Okay,
So
let
GH and HAI. Okay. Okay.
you get the point N by the intersection of these two circles.
Okay.
Now you take the circle JNI and GNH. Define then this is true for A and B as well. these new nicely defined points. Ma into mb is equal to ms into mj is equal to mg into mi, and they have the same angle bisector. And in the special case when they're I iso, this is a special case and where the A and B are isogonal conjugates of this general result. On that note, I'll conclude. This is for you to prove.
Okay.
Yeah, we'll end with a blank GGB as we started. Yeah, any questions? Anything?